Okay, let's get into it. We're doing deep dive today, really aiming for, total mastery of the core ideas in machine learning, AI, ML, DL. The goal is to get you up to speed fast so you can confidently follow pretty much any technical chat on the topic.
Right, and to get that solid footing quickly, it helps to start with the hierarchy. I like the Russian dolls analogy. Think of AI as the biggest doll. It's the grand goal, right? Creating intelligent systems.
Okay.
Then nested inside, you've got ML, machine learning. That's the main way we're actually doing AI nowadays. Learning patterns straight from data.
And the innermost doll.
That's deep learning, DL. It's basically a very powerful, sort of sophisticated tool within ML that uses these big, deep neural networks to do the learning part.
Got it. So ML is kind of the engine driving progress in AI. And its big contribution is finding these complex patterns, and this seems crucial, being able to generalize them, to apply them to new stuff it hasn't seen.
Exactly that. Generalization is absolutely key. And how it learns those patterns, well, that really depends on the data you give it and the kind of feedback it gets. Our mission, to cut through that jargon, we're focusing on the hierarchy, the key trade-offs, and the why behind it all.
Exactly. We want to give you that mental map you need for mastering generalization.
Okay, quick rundown on learning paradigms. Supervised and unsupervised seems straightforward, data-driven. Labels or no labels.
Right. Classification, regression with labels, clustering without, dataset focused.
But reinforcement learning, that's the odd one out.
Totally different beast. It's not about a fixed dataset. The agent learns by doing, interacting with an environment, getting rewards, getting punished, basically.
Yeah.
Think robotics, game AI.
So the interaction part. Is that why it's maybe trickier to get working reliably compared to supervised?
Oh, definitely. Much less stable sometimes because the target isn't fixed. But okay, let's stick with supervised models for now and hit the absolute core issue, generalization.
Right, making sure the model works on new data. And this is where the bias-variance tradeoff comes in. You said this is critical.
The most critical concept for generalization, I'd argue. It governs performance on unseen data.
So let's break down the total error. What are its parts mathematically?
Okay, so it's bias squared plus variance plus, and this is important, the irreducible error.
Irreducible error.
Yeah, think of it as the baseline noise. The randomness in the data itself that no model, no matter how good, can eliminate. It's just there, the messiness of the real world.
Makes sense. So you can't aim for zero error. Okay, the dartboard analogy helps here. High bias, underfitting. That's like all darts landing together, but way off the bullseye.
Exactly. Consistent, but consistently wrong. Systematic error.
And high variance, overfitting.
Darts scattered all over the board. The model learned the noise, the random fluctuations in the training data, not the real pattern.
So we need to balance them. Find that sweet spot of model complexity.
That's the game. Minimize the sum of the two.
Which needs a process to find that minimum. That brings us to optimization, gradient descent, or GD. The blindfolded person walking downhill analogy.
You have stepping opposite the gradient towards the lowest point of the cost function. Simple idea.
But we don't usually use plain GD, right?
Not for big data sets, no. The standard is mini-batch gradient descent, MBGD. It's the practical choice.
And why is that?
It's a compromise. More stable than stochastic GD, which uses just one sample that's noisy. Faster and more efficient than batch GD, which uses the whole data set that's slow. Mini-batch gives you a good balance, plus it works great with modern parallel hardware.
Okay, optimization sorted. Now, something crucial for deep learning specifically, non-linearity. Why is that essential? Why can't deep networks just be linear?
Good question. It boils down to math. If you only used linear activation functions, stacking layers, even hundreds of them, it would all mathematically collapse.
Relapse.
Yeah, it becomes equivalent to just having a single shallow linear layer. You lose the whole benefit of depth. Nonlinear functions like ReLU are what allow the network to bend and curve to learn those really complex decision boundaries you find in real data.
Without nonlinearity, depth is pointless. Got it. Okay, final piece. Regularization. Fighting overfitting. That high variance problem. L1 versus L2.
Right, key tools. And the geometric view really helps understand the difference. L2, ridge regression, its constraint is like a smooth circle. It pulls weights towards zero, shrinking them.
Towards zero, but not necessarily to zero.
Exactly. But L1, lasso, its constraint is a diamond. Sharp corners. right on the axis. And because optimization often hits those corners.
It forces weights to become exactly zero.
Precisely. That's L1 doing automatic feature selection. It creates sparse models by zeroing out less important feature weights. It's the geometry doing the work.
Fantastic. So the 3 pillars: generalization through bias variance, optimization with mini-batch GD, and nonlinearity enabling depth. That really covers the core concepts.
It gives you the framework. And maybe one final thought, shifting to validation.
Go on.
The absolute integrity of your final result depends on one piece of discipline. Never, ever use your test set during model tuning or development. Keep it locked away until the very end.
Because otherwise you introduce look-ahead bias. You're implicitly tuning on the final evaluation data.
You got it. That final test score becomes meaningless. The method of validation is just as crucial as the model architecture itself. Remember that.
But always remember, the first step is diagnosing the error. Knowing the problem dictates the solution.
That definitely clarifies the core mechanics. Okay, here's something to think about as we wrap up. Even if you follow all this, you tune your model perfectly, why is relying on just one single split of your data into a training set and a test set actually a pretty unreliable way to estimate how well your model will really perform out there in the wild? Think about the variability that single split introduces. We'll leave you with that.